You have the third lecture by Xiaoming Mao. Go ahead.
Okay, thank you. Yeah, good morning, everyone. So today we're going to be switching back and forth between slides and the Blackboard. So the outline is roughly going to be, we first do a little bit of recap for, so technically this is my slides for lecture 4, but I'm switching the order a little bit according to the feedback I receive. So we're going to do some slides and some of the prepared lecture, the Blackboard material. So basically, we will first continue our discussion of the finite frequency topological states from the 1D chain. And today, we're going to talk a little bit about 2D systems. And I will then show you some slides of experiments and theory, just to give you a flavor of some examples that has been proposed. And then we will go more into Maxwell lattice topological mechanics. I will try to provide you with a more or less unified picture that puts together the finite frequency topological states that we talked about and the zero frequency topological states in Maxwell lattices. So that is basically what we will do today. And then tomorrow we will sort of get closer to the theme of this school. We will talk about the aperiodic networks, whether this kind of topological states could arise in disordered or quasi-crystalline systems. And maybe if we have time left, I'll talk a little bit about the rigidity and any topics that like people are interested in. Okay, so let me first recap what we talked about yesterday in terms of 1D chain. So here I think I opened a paper which has nice figures, better than what I drew yesterday. So remember we talked about this 1D chain with 2 types of springs, right? You can all see that. And then we talk about when the 2 spring constants are equal, the band close. In fact, you actually have a smaller unit cell. You can unfold the Brillouin zone and just get 1 band, right? And then when you make the 2 spring constants to be different, and this beta is defined as this, the difference between K1 and K2, right? So when beta is positive, that means K1 greater than K2, and beta negative means K1 less than K2. And we talked about that in this specific case, you have this so-called phenomena of band inversion, which means if you look at this lower band, around 0 momentum, the acoustic branch is such that 2 of the atoms in the unit cell are moving in phase. But when you move to the edge of the Brillouin zone, they become opposite, right? And the sort of the acoustic branch of the moving in the same direction becomes the higher band. So there is some inversion occurred in the middle, and that is well captured by the phase of this Z, which is the off-diagonal component on the 2x2 Hamiltonian, okay, or the dynamical matrix. And we talked about defining the Berry phase and the integral to get you the so-called Zach phase, and use that to define a topological invariant, which is 1 for this case and 0 for this case. And I think I got some very nice questions asking, like, what is the difference between these 2? They are just shifted by 1 spring, right? And they are actually, so although it looks like this is 1, this is 0, this looks like non-trivial, this is trivial, but they are just related by either a reflection or a shift by 1 lattice, not half of the lattice spacing. So what is really important is when you have an interface between these 2, you will get an edge mode. You can rigorously prove it, which I'm skipping now. So we can just say more pictorially. Let me see, I think they have a figure. Yeah. So you have band opening when K1 is greater than K2, when K1 is smaller than K2 in different ways. When you introduce an interface in between, you have to close the band. So there is a mode in the at the interface. And here, this paper includes nice figures of computational result of what the modes look like. So when you have, I think these 2 figures are the cases of think one of them is from positive. Oh, yeah. So here, this figure is as you change the value of beta. So remember, beta is K1 minus K2 divided by K1 plus K2, right? So on one side is the band opens in one way, and in another side, it opens in another way. And then you can create an interface like this. So on one side, this interface has spring constants that is, let me see, beta is greater than these two. And on the other side, these spring constants are smaller than these two. So anyway, you have a mirror symmetric interface, right? And then you see that in these two different cases, you always get one mode in the gap. In one case, the edge mode look like this. So this axis is spatial direction, and n equal to 0 is at the interface. So remember, on Tuesday, I asked you to do a numerical experiment on your own to just solve it in real space. If you do that, it's going to be something like this. You solve for the real space eigenvector, you will find that there is a mode in the middle of the gap like this, and on the other side, it's something, sorry. I think it's this one is this one. This one is this one, okay? So anyway, that was what we talked about on Tuesday. Any questions about any of these? Yes?
Why is it not symmetric in beta?
Yeah, that's a very good question. So it has to do with the detail of the interface. And what you know for sure is that there is a mode in between the two bands. But where it is has to do with the detail of the symmetry at the interface. We are going to talk a little bit about that today. Okay? There is a symmetry protection for this. Any other questions? Is the phenomenology clear?
I have a question.
Yeah.
When you say that there is this interface and then it has this topological mode,
Yeah.
how does it look like? Because the normal modes I see quite well.
Yeah.
And how does this one looks like?
Yeah. So it is a normal mode of the system. So if you say you do a 100 site chain numerically, 50 on this side, 50 on this side. So I alternated the A and the B. And then numerically you solve for the eigenmodes, you will see this. So basically, if you have 100 sites, you're going to get 100 modes, right? It's basically, I think, half of them here, and then one mode here.
Mm-hmm. I see.
Okay? And all of these other modes are plane wave states like this. It's only that one is localized. Okay? Okay, so we will leave it there. And today I have a little bit of Blackboard stuff to talk about how this generalized to 2D, and actually you get a more robust index. Okay? So let's start from this dynamical matrix we defined for the 1D chain again, and use this as a starting point. So remember we defined this 2x2 dynamical matrix. And remember we said that this is a Hermitian matrix. And for all 2x2 Hermitian matrix, you can write it in the so-called Dirac form. Right? You can write it as D dot sigma. So sigma are the Pauli matrices. So sigma x, sigma y, sigma z. I suppose you all have seen this in quantum mechanics, right? So for all 2x2 Hermitian matrix, so there should also be an identity part, which we will just drop because it's just a shift of the whole spectrum up and down. So you have 3 free variables, which are the 3 components of D. So you can write it like this. Is it clear what we are doing here? So then just to be complete, I will write the matrices here to remind you. Okay, so we can decompose this 2 by 2 Hermitian matrix into these 3 components. And dx, dy, dz, you can pretty easily write it down. Dx is k1 plus k2. Sorry, this is d0, so let me write it. I will just be complete. So there is a d0 plus identity and then plus this, right? So d0 is k1 plus k2. But we're going to drop it in the following discussion because it's a trivial component. Okay, is it clear how this works? So you multiply each with the components and you get back this matrix. Okay, so then you see that this is actually a very nice way to think about the problem. What it does is that it maps this Hamiltonian, which was in K-space, now into 3-dimensional vector space of dx, dy, dz, right? So any 2 by 2 Hamiltonian, 2 by 2 Hermitian Hamiltonian running out of space end up in a point here. Okay? Is it clear? We just map it to a vector dx, dy, dz. And you can actually rescale so that it is only on the unit sphere, right? So then this provides a really convenient way to think about what it means to define a winding number. This is the sort of the geometric basis to think about this type of winding number. So as I mentioned in the last class, there are many, many different types of topological states. We are only talking about a tiny fraction of it, just to give you like a very elementary example. Okay, so how does this work, right? How do we actually make use of this sphere? It's sometimes called the Dirac sphere. So let's now think about how do you calculate, how does this notion help you calculate the Berry curvature, okay? So remember last class, we defined the Berry connection. And when you integrate the Berry connection over the first Boolean zone, you get that winding number, right? We defined the Berry connection, which is a vector A here, this psi is the wave function. So remember last time we solved for the wave function, and we find that this whole wave function is just controlled by this complex number z, right? Which end up, which now is expressed in terms of actually dx and dy, right? And then the Berry phase, which is the contour integral of this connection. Now can be written in the D space, right? So we can consider, basically, the picture is that we now have a mapping from K to D. Is it clear? So for any given value of momentum, you get a Hamiltonian, and that Hamiltonian can be written into a vector D. Okay, you had a question?
Is that figure a representation of the
So yeah, use a mic, yeah.
Is that figure the representation of the specific case that are on the left?
Oh, yeah,
Because,
so this,
because the last component is 0
Okay.
and
yeah,
the
that's right.
figures.
That you're right. For this particular case, I'm only taking points on the equator. That's an important point we are going to get back to. But in general, if you actually have a DZ, it can be anywhere. So if you have a bias between this and this, it can be anywhere. Yeah. Any other questions? So now if we want to calculate this in D space, what can we do? So we said we want to go from K space to D space. Right? Each K maps to a D. Let's see. I think it's just my computer go to. It's OK, we're not using that for now. So can we turn this integral into the D space? You need to what?
We need to map the wave functions as a function of k. We have that last night, right?
Right, so we have the wave function. Oh, I think I'm mixing the notation a little bit. Q and K are the same thing. So K is the same as Q. Same K and Q. Okay? So when you look at this formula, you will see that you can actually write it in a different space without doing anything, because here is an integral over momentum. And in A, you have a derivative over momentum. When you do a change of variable from K to D, the Jacobian will cancel out with one another. So you can just write it as an integral in D space, right? Oh, no, this is not a 3. Okay? Is it clear what we are doing? And then you can use Stokes' formula, right? Because this is a line integral. You can turn that into a surface integral. What you have is that this is going to be so what we are doing is that suppose we are doing this integral along some kind of contour in D space, right? Suppose the Brillouin zone, for example, maps into such a circle, this yellow circle on the sphere, okay? And we need to do the integral of our Berry connection over this path. But then you can turn that into a surface integral of this cap enclosed by that path using Stokes' formula, where this B is the curl of A. B okay, the curl of A. So if this is in D space, then it's the curl as a function of D. Okay. So
Xiaoming,
yes.
I'm not sure if I followed. Why do you need to go to D space to do this?
You don't need to. You can do this in K space too. So
Okay.
so you can, if you have a two-dimensional Brillouin zone,
Yeah.
you can also write this into a 2D
Yeah.
integral in Q space.
Okay, okay.
Yeah.
Okay.
So exactly like that. So you can ask, what's the benefit of doing this, right? The benefit is that the Berry curvature in this representation is homogeneous on the sphere. It makes the calculation really easy. So if you do a careful calculation of solving wave function as a function of d, you will find something like psi of d equal to this. Where theta and phi are the polar angles in the d space. So remember, for this point, you can have a theta and a phi, which is on the circle, right? When you solve for the wave function, you will find something like this. And of course, here, you can choose whatever gauge, right? And for the, you have two eigenvectors. Each of them, one, as you can look at this formula, it is actually the local tangent vector at d. And the other wave function is the local tangent vector at minus d. And you can choose whatever gauge between them, okay? So that's I don't want to go into too detail in solving that. But when you plug this into the calculation of Berry curvature, you get, sorry, this is Berry connection. The Berry curvature is B. This A is Berry connection. Okay? When you plug it into the formula to calculate A and B, you find that B as a function of D takes this simple form. Okay? And the plus and the minus are for the upper and the lower branch of the two wave functions. Okay? So now you see that it takes a really nice form. It is just a normal pointing out, right? And you get the same value everywhere on the sphere. So then what does this integral turn into? This integral I'll give you a minute to think about it. So if you plug this into this integral, yes?
No, I'm just thinking.
Oh, okay. Yes. Yes.
You have two surfaces bound the loop where you are evaluated your Berry phase. If you add these two flux, you get
Yeah.
integer number. Let me say like that.
Because you mean why?
Really, there is no this loop. There is no one single boundary surface for the loop. There is the upper surface. There is the lower surface. If you add both surfaces, you get 0 because you don't have a loop on the sphere doesn't bound any surfaces. There are two surfaces that is bounding.
Oh, I see what you mean. So you mean I have the surface on this side and the surface on this side. So when you use the Stokes formula, when you choose the direction of this contour, you choose which surface it is, right? And when you there is outward normal, right? That makes it well defined.
The normal are into positive sense for the two surfaces.
Yeah, you get the same answer whether you choose this and this. Okay? Okay. So what was the answer to this integral? It's a solid angle. It's actually 1/2 of the solid angle. Okay? So this shows you that when you calculate the Berry phase along any contour, it turns into a solid angle in this D space. Okay? And then you can ask, what does it mean, right? Why do we say you have to get an integer? Right? It looks like if you just do an arbitrary case, you can get any answer, right? It doesn't have to be a 4 pi or 2 pi or anything, right? So firstly, you have to, we need to talk about it in different cases. First, in the 1D chain, we saw in 2 cases where you get Zach phase 1 and Zach phase 0, where Zach phase, if you translate into what we are calculating here, it is the solid angle. Let me see what is the factor of 2. I think it is the solid angle over 4 pi. Okay? And remember, when we actually calculated in last class, we find that it's either 0 or 1. What makes this an integer? If it looks on that picture that you can get an arbitrary path, why does it have to be an integer? No, I think this is 2 pi. Yeah, it has to do with this special condition of dz being 0. So what does dz being 0 mean? It means, yeah, you're only choosing the equator. And then when you choose or in other words, all of the points of this Hamiltonian can only map to points on the equator, right? And then when you map to points on the equator, what are the cases it can happen? Or what are specifically the case that give you nu equal to 1? What is the case when it's 0? Exactly. So this is the case where you go around the Boolean zone, you get a full circle on the equator. And then when you do the integral, the solid angle is 2 pi, and this nu becomes 1. And this other case, something happens like you go this way and then turn back. So this path is when you take k equal to minus pi over a to pi over a, right? You don't finish a full circle. And then this becomes 0. Does that make sense? So in order for this to be taking integer values, you need dz equal to 0. And this is actually, this has a name. This is the so-called Chiral symmetry. So in this sense, sometimes people call this type of topological states to be a symmetry-protected topological states. Because if you don't have this symmetry, if you can arbitrarily change the value of dz, then you have a circle somewhere you don't know, right? And then with a little bit of perturbation or something, you can just pull it off. There is nothing stopping it from shrinking to 1 point. And the Berry phase just turned to 0, right? However, when it's in this case, no matter what you do, as long as you keep this symmetry, the points of k mapped onto points on this equator could shift a little bit. Sometimes you have more points on this side. Sometimes you have denser points here, less dense points there. But you cannot change how many times it winds. And that's the idea of topological protection. Okay? Any questions? Yes?
What prevents it from doing multiple windings?
It can.
And then we can, okay.
It can. So just in this case, you only have 2. Yeah. Yes?
So can you give an example of a system that doesn't have this symmetry and that has a DZ not equal to 0?
Yeah, that's a very good question. Can you think of an example? What would you do to this 1D chain to make this non-zero?
Right. I mean, you said that you have to have a difference between the
Yeah.
diagonal terms.
Yeah. What does that? Yeah. Can somebody design a system that has a non-zero DZ? Yes. Yeah, please use the mic so everyone can hear. Yeah.
I guess you could attach every mass to a single. You would need to break the symmetry between atoms A or
Yes, that is one
nodes
way.
A and B.
Yeah.
I guess you could do that by giving them different mass or different stiffness to the ground, something like this.
Yeah. So those are 2 ways where you can do it. One is, like you said, you just pin a sublattice to the ground, which correspond to adding some term here, but not here, right? The other is to change the mass. So what we write here is a dynamical matrix. It doesn't have mass in it, but the actual Hamiltonian, when you write the m omega squared, m will be there, and making them to have different mass will break that and make it not protected. Okay? Yes?
But in reality, these are not perturbations that are hard to get, right? So in reality, the symmetry will never be strictly enforced, right?
Yeah.
So to which extent are you topologically protected? I guess there's some scale, right?
Yeah. So if you don't strictly have the symmetry, you just sort of gradually break it, that edge mode will gradually merge with the other bulk bands. So this is sort of the non-robustness of these kind of symmetry-protected topological states. If you don't perfectly have that symmetry, who knows, right? You may have the mode or you may not. It depends on the detail, macroscopic detail of the problem. Okay? I don't know if anyone else have ideas or anything related to this. Yes?
What consequence came when you broke this symmetry in the eigenvalues? What consequence have break this symmetry in the eigenvalues of the matrix?
In the what?
Eigenvalues.
Eigenvalues.
In the eigenvalues, when I break the symmetry, yeah. So when you break the symmetry, so you will, the path of K going around the Brillouin zone may not be exactly at the equator, right? You may still have a non-zero value when you do this integral, but it's not guaranteed to be an integer, right? And then when you go to calculate the mode, it's not clear whether you should have an edge mode or not. If you're approximately having that symmetry, maybe the mode survives for a while. It depends on the detail of the problem.
But it's going. This mode if it exists, it's not a topological protected mode, right?
So it's a symmetry protected topological.
Yeah,
mode.
but
Yeah.
if I broke this symmetry,
Yeah. It's not, yeah. Okay. Any other questions? And then coming back to the question you asked about why one mode is in the middle, the other is not, it has to do whether this symmetry is protected at the interface. I do not know the full detail, but I think it comes from there. Maybe that paper I referenced talked about that, I think.
K2 is not 2K1s next to it. Something better was going in that direction. You had a larger band
Right.
around the edge.
Yeah,
So you have a simple the choice of the edge.
the choice of the edge.
Whether it's a K2 edge or K1.
Yeah. It is that difference, yeah, but I'm not sure how it exactly works there. Yeah, okay.
I have another question
Okay.
about symmetry. So Chiral symmetry is one example of symmetry that protects your edge modes. Do you have other examples of symmetries in the 1D chain, like other symmetries beyond the Chiral symmetry?
They are, yeah.
Could you use your 1D chain to illustrate more than just the Chiral symmetry?
So in this particular model, it has time reversal symmetry, right? I'm not sure if there is anything interesting I have here. I'm not sure if I understand your...
How does time reversal symmetry protect?
Oh, you don't need a time reversal symmetry to protect this state. I think time reversal symmetry determines which class this is in. Right. Okay. Yeah, I have to admit that I'm not really have deep expertise in these finite frequency topological states. I'm sort of trying to give you a simple overview of the field, but I do not claim I know all of the answers. Okay, so your help for answering each other's question is very welcome. Okay, so let's now think about what happens in 2D, right? In 2D lattices, what is the topology of the Brillouin zone? So in 1D, this 1D lattice, right, the Brillouin zone is a circle, basically. And then the mapping is putting a circle on a sphere. And just like what we said, if you don't have this symmetry, putting a circle on a sphere is trivial. You can always shrink it to one point, right? You need this symmetry to say I can only be on the equator, then I can have non-trivial 1D number. But in 2D, it's different. In 2D, what is the Brillouin zone? You have a kx and a ky, right? And let's just think about the simplest square lattice case. You have a Brillouin zone like this, right? But this edge is the same as this edge. And this edge is the same as this edge. If you wrap it together, what do you get? It is a torus, right? Is it clear? So you wrap these two edges together, you get a cylinder. And then you wrap it around these two closes, you get a torus. So the mapping is really now from torus to this sphere. You want to use the torus to cover the sphere, right? So this is your K space. This is your D space. For each K, you have a H of K, right? And each of the H of K ends up as a point on this space. So what winding do you have? What are the topologically distinct way to put this on this?
Can you ask the question again?
So how many topologically distinct ways can you map or wrap? This is T2 is 2 torus to S2. S2 is the surface of a sphere in in 3 dimensions. So topologically distinct ways means that there are, so this is really like using concepts from the so-called homotopy theory, which has to do with wrapping one object to another object, and you have equivalent classes of, for example, you can wrap one sphere on another sphere. There are many ways of wrapping so that you cover it once, but they differ in details, right? I can deform one sphere a little bit or deform the other sphere a little bit, but the time you cover it is always integer, right? So these different ways, the ways that you don't change how many times you cover are topologically distinct. The ways that, sorry, I think I said it wrong. The ways you don't change how many times you cover are equivalence classes. And the ways where you actually change how many times you wrap around are topologically distinct. Now we are interested in understanding what is the algebra when you try to describe how many times can I wrap a torus on a sphere. So one trivial case is that the sphere is outside of the torus, right? You just get 0 winding. And when you do that integral, you get 0, right? Can you think of another case? The first one is the sphere is outside of the torus, so you don't wind at all, right?
I'm not sure I understand. So how do you map the points when the sphere is outside the torus? Do you just do projections? Or, I'm still not seeing how you don't get multiple points for the same point on the sphere.
It doesn't have to be so 1 point to 1 point. Yeah. So this turns out to be counted by integers. So it maps to z. So you can have 0 times, 1 time, 2 times, 3 times. It can be infinitely many times. It's sort of abstract to think about how it works, but I think people have rigorously shown that this maps to integers. Yeah.
Why is the D space still a sphere, not something higher dimensional?
What?
So the D space, it's still a sphere in this case? We are mapping onto a sphere?
Yes.
Yeah, but why is it a 2 by 2 still?
Oh, yeah. Yeah, here we are just talking about the 2-band models. You can have higher. So as I said, I'm just talking about a very tiny part of all of the possible states. So we're talking about the 2-band models. Okay. So you can have integer times of wrapping, and that corresponds to the Berry phase, the winding number or the churn number. This z is the churn number. So it is basically the degree of the mapping. This is so-called the mapping. How many times is the so-called degree of the map?
Xiaoming, this is nothing necessarily to, you cannot do this by continuously deforming, right? Then you need to have another type of mapping. Because if I want to deform this torus in a sphere,
yeah, it's
impossible.
not a continuously mapping.
Okay,
it is counting the number. I don't know what's the mathematical term for that. I think it's counting the number of cover, how many times you cover.
You mean how many times you are able to cover the torus within a sphere? Is it right?
How many times you can, use the torus to cover the sphere?
Ah.
Yeah.
But it would be enough to calculate the surface of the torus and then see how many times it fits in in a sphere? Oh no. This is
It is a mapping that it does not preserve the area.
okay.
So yeah. Yes.
When I think of the first homotopy group, you can draw loops on the space that you're trying to cover. And this is the second
Yeah.
homotopy. So the mapping seems kind of backwards because when you draw loops on T2, for instance, you're mapping S1 to points on T2.
Mapping, sorry, what's the last thing you said?
I'll think more about it. But you have T, like a time parameter, that goes from 0 to 1, say, that parameterizes your one-dimensional curve that lives on T2, for instance. So that's a map from S1 to T2. Well, I'm just talking about the first homotopy group. But I'm trying to abstract that to the next, but I don't know. Okay.
Yeah, so I don't know, you had something you want to say? This is pretty abstract, and again, I'm not a real expert in this, so I just want to sort of give you a cartoonish picture. If this is too sort of abstract to think about, the 1D case, mapping a circle to another circle is much easier. So I will just draw a picture to illustrate that. So if you have a 1D chain, remember we said the Brillouin zone is a circle, right? You go from k equal to minus pi over a, 2 pi over a, you go around this circle. And then you map it to this equator, right? Map it to this equator on the D space. I'll just draw it as a solid circle like this. Here, it's much clearer that it maps to integers z, right? Because you map each point from this circle to this circle. Z equal to 0 means that I just cover part of it and I go back. And 1 means that I use it to cover once. And 2 would mean that I do like this, right? Yes?
Aren't we trying to cover T2 with the N sphere? So the first homotopy group, we're taking loops and putting them on our space.
Mm-hmm.
And the second one, we're taking 2 spheres and putting them on our space.
I'm not sure. Yeah. Okay, so this is roughly what I want to go like as far as I can with the Blackboard. And next I'm going to show you some slides with pictures from experiments and show you like we took all the trouble to do all of this. What do we gain, right? What are the edge modes and what do they look like? And if we have time, so we have about half hour left, right?
40 minutes.
Okay, yeah.
I have, I don't know, maybe it's a silly question, but in the lower dimensional case, we could distinguish between perhaps loops winding in different directions, clockwise, counterclockwise. Is that equivalent for the surface mapping? So how do you get
the
negative
different directions?
Negative numbers there?
That's a good question. I do not know the answer.
Okay.
I don't know if anyone. Yeah, it has to do with the orientation, I think.
You mean the rotation of the surface of the torus relative to the sphere?
Okay, so I will do the slideshow from here. Okay, yeah, so this is just a recap of what we just said. I think we don't need to necessarily go through all of it. We talked about the 1D chain, the bulk gap, and the winding number, and you generalize it to all two-band models. So I forgot to emphasize, this is two-band model, so you have a 2x2 Hamiltonian, which can always be mapped into this sphere. And then the important problem becomes this mapping. Okay, so the Chern number is the degree of mapping. So next, I would like to just show you a few examples. So this is a figure probably many of you have seen, right? One of the earliest work of topological mechanical states where you have one-way transport. So I'll first play the video, and then we analyze a little bit of what's going on. So this is a lattice made of gyroscope. So in each of the gyroscope, there is a little motor so that it is spinning. And then you have coupling between the neighbors in this hexagonal lattice arrangement. Okay? And then what they show is that when you now excite a wave on the edge from here, the wave only go one way along the edge, which is really amazing to look at, right? And the colors, I think, help you to pick up that these gyroscopes are rotating more than the ones in the bulk. And they also have nice demonstrations of like, if you remove one on the edge, the wave will just go around there. So it is really like a very robust topologically protected object, this edge mode. And this is another paper that came out almost the same time, but it's a theory paper where they proposed a very similar model with also one-way edge states. So what is going on in this problem? So without too much detail, I will just sketch. So if you think about what is the equation of motion for these gyroscopes, right? You can write this for each gyroscope into something like this. So you have a first-order time derivative of the axis of that gyroscope. And then when there's a force on the gyroscope, how it affects the motion of that axis is through this equation. So the velocity generated by the force is going to be perpendicular to the force. And you have a first-order time derivative equation of motion. And that allows them to map it to a quantum Hamiltonian, where the equation of motion is like this, and they have a 4-band quantum Hamiltonian. And then the two middle bands have this phenomena of having the Dirac cones closing when the lattice has a geometry like this. And then when you distort the lattice into the honeycomb or the so-called reentrant honeycomb, you open the band in two different ways. And in this case, you have an edge mode that go clockwise. And in this case, you have an edge mode that goes counterclockwise. And this is a lattice where they broke time reversal symmetry, and you only have edge modes going in one direction. So no matter how you perturb the system, it always goes this way. Okay? So this is a very desirable property in terms of designing metamaterials, because it's obviously a good thing when you can control waves to only go one way, not the other way, the so-called non-reciprocal behavior. Okay?
I have a question.
Yes.
I'm a little bit confused by this. When you say gyroscope, then each node can, the way that it vibrates, not vibration like in this direction, but it's really some turning. The nodes are able to make, not only to vibrate as I may use it, but it can also turn around itself. Is it right?
Yes, so if you look at the detail here, let me see. So the rotor is inside of this container. So they rotate, but that rotation doesn't affect the coupling between them. It's covered in that little box.
So you have the spring that connects the nodes, but inside the node, we have the rotors?
Yeah, that's right.
Okay.
Yeah. I think they probably used some magnetic interactions to mimic the spring. I don't remember the detail. I don't know if anyone knows. Okay, yeah. Okay, so this is the first case where you break time reversal symmetry, you get these one-way edge states. And it is this type of topology, basically, okay? And then I think there has been new proposed experiments where you say that breaking time reversal symmetry is pretty complicated in a mechanical system, right? Can we do something purely passive? So there are various proposals. Here I'm just including one example, the so-called Valley Hall effects, where you don't break time reversal symmetry, and as a result, I think I included, oh, I didn't include that. So when you don't break time reversal symmetry for these 2D systems, one property you get is that the Chiral number for each band has to be 0. But you can have like this non-quantized covering of that sphere at K and K prime in the second Bernoulli zone, so that you have you introduce asymmetry between the two sides on a honeycomb lattice, and you break the gap at both K and K prime, but they have opposite Barry phase, so that you get these edge states. So here, as you can see in this example, can you see the cursor? Yeah. So you have two lattice domains where you break the symmetry in different ways. I'm not sure for this experiment, but one thing you could do is in one domain, you make A heavier. In the other domain, you make B heavier. And then you get the wave that propagate along this edge between the two domains. But this is not a one-way propagation. It goes in both directions. Okay? So this is another example. And just one more example I would like to mention is the so-called AAH model, which is the Aubrey-Andre-Harper model. So here, this is the original tight binding model with a periodic potential. So basically, these are the hopping terms. If you think of a quantum tight binding Hamiltonian, these are the hopping terms. And then you have an on-site potential that is periodic. But the periodicity of this potential doesn't have to be, what's the word? Commensurate. Yeah. Doesn't have to be commensurate with the lattice. As you can see here, the periodicity is somewhat a irrational number times the lattice. And you can solve this, and when you want to translate it into a mechanical problem, you just basically replace this with m omega squared. It can be a equation of motion of the second order time derivative equal to, these are the springs left and right, and this is some kind of on-site potential, right? So you can think of this as a mechanical chain of springs, and then there is on-site potential that is not necessarily commensurate, right? So the origin of this model has to do with quantum Hall effects in 2 dimensions. So you know, when you first study quantum Hall effects, it's in continuous space, right? You can ask what happens when you put a lattice in a magnetic field. And then the model basically simplifies into something like this. So remember, when you solve it in continuous space, you can choose the Landau gauge, and you get in one direction, you have plane waves, and the other direction, you have harmonic oscillator, right? It's similar thing, but when you have a lattice, you have discrete, you have to consider the discreteness of the second direction, and you get this potential that comes from the momentum in the transverse direction. And then it acts as a potential on this effective 1D chain problem. So anyway, this model has an origin in a 2D lattice problem. And then the solution of the spectrum is very interesting. So that's the so-called Hofstadter butterfly. Probably many of you have seen this picture, right? So what is this figure? This axis is the parameter of theta here. So basically, I change the wavelength of this potential. And for each given wavelength, I calculated the spectrum of the lattice. Right? Then you get a sequence of dots here. Each of the dots, as you make a vertical cut, are the eigenfrequencies of this Hamiltonian. And you change the value of theta, you get a graph like this. Is it clear what's going on? And why it looks this weird shape, right? You can think about if this theta is commensurate with the lattice, what you get should be clear bands, right? You should get a unit cell and you get bands. And these are special points along this curve. But there are infinitely many points in between where it's irrational ratio. And what you get is a fractal spectrum. That's why it looks so weird. You have like a dust in there, right? And yeah, so that's the basic spectrum. And then why are people interested in this in terms of topological mechanics? What happens is that there are edge states between these bands. So basically, you can draw the spectrum in a different way. So I can choose any value of theta here. I just make a cut here. Then I get many bands, right? And then between the bands, you get these edge states. And then you can calculate the Chern number for each of the band. That tells you whether the edge state lives on the right or lives on the left. Okay? This gives you a very interesting control of the system. If you can change the value of phi, oh, sorry. Did I mention what is phi? So phi is the phase. So it's like you change theta, you change what is the wavelength of this potential. You change phi, you change the phase. You just shift it relative to the lattice. And by doing that, that edge mode evolves. It starts from the bulk, and then it goes, and then go to the other band. And then people proposed various models of making use of this effect to do the so-called adiabatic pumping. So pumping means that you give it a signal, and by how you control the system, you can control whether the signal go to the other end of the lattice or not. Okay? So this is one example of an experiment that realized adiabatic pumping. So as you can see, they have, it's an acoustic system. So they have these tubes. And interestingly, they have two rows of these tubes. So in each of the row, they are equally spaced. It's periodic. But when you couple the two rows together, you add up these two periodic potential. When they are not commensurate, the added total potential is a periodic potential that's incommensurate with the spacing of these points. Okay, so you can map it to the AAH model. And then the nice thing about this system is that you can slide the two rows relative to one another and change this value of, change the phase of that change the phase of that periodic potential. So then what happens is that they can give the signal here and then shift the two rows relative to one another. This edge mode becomes a bulk mode and then comes out from the other edge. So it's a pretty cute effect to demonstrate. So with that, I would like to just finish this part of the discussion. Again, just to emphasize, I'm just talking about a tiny fraction of all of the, even for topological mechanics, there are many, many papers that I did not mention at all, and not to mention like the whole topological states. And then there are a number of reviews I'd like to recommend. There is this review by Sebastian Huber, which was on 2016. It's a very good review. It's a little bit old. And then there are a number of newer reviews that give you like the more of the new work of the field. Okay, so that's, with that, I would like to have a little more time. I will next talk about the Maxwell lattices. But before we finish this, any questions? Yes?
we think about to see something related to the under-localization phenomena in this one-dimensional model. You have written the Schrödinger equation for the electron in the lattice in a regular lattice.
Yeah, so are you talking about the...
this. And you map your equation in this equation for the two-dimensional quantum Hall states. If you consider a random lattice, what would be the effect in the quantum Hall equation?
You mean if you consider a random lattice?
Yes, that's to see the under-localization phenomena, something like that, in the context of the Hall state, quantum Hall states.
That's a very interesting question. I think that's probably studied, but I do not know. So I don't know if anyone else know what happens when you have disorder in this problem.
Yes, exactly that.
Yeah.
That's what I'm asking.
Yeah, how it interplays with with the edge states.
Generally, I'm asking about the interplay about the topology and disorder.
Yeah, I think there has been studies on that, but yeah, I have to look at that to answer. Yeah. Okay. Yes.
Could you return to the 2D lattice and discuss the breaking of time reversal symmetry in that model, in the mechanical model? Why do you get a single direction of propagation, essentially?
Why do you get what?
A single direction of propagation, or am I?
So the direction of propagation, I think it comes from the Chern number. And you break a time reversal symmetry that allows a non-zero Chern number in the 2D lattice. And that determines the direction. Yeah, so in the electron problem, that is introduced by the magnetic field. But here, it's introduced by the motors. Yeah. That shows up in this thing. You have to break time reversal symmetry in order to have an equation of motion like this.
I have a comment. You have a nice review paper with Tom Lubansky on annual review of condensed matter
So
physics.
yeah, I did not include my review there because my review is primarily on Maxwell lattices. So here, that list are reviews of these finite frequency or primarily on finite frequency topological states. Yeah, I have a more full list. I think maybe I can just flash it of reviews, references that I think it's posted on the website. So there are references for lecture 1, where we talk about rheology, and lecture 2 and 3. Oh yeah, I would like to mention that on lecture 2, I talked about these geometry of vector bundles and how that related to topological insulators. These are all from this very nice, really recent, I think it's 2022, but whatever. I think it's a very recent review. It's a set of lecture notes from this. And of course, there are textbooks and review articles on topological states, which you can find everywhere these days. And the 1D chain paper is this one that I showed. Okay, sorry, I think it's this one that I showed on the in that PDF file. So this is, I think, posted on the web page.
Xiaoming?
Yes.
Can you say a little bit about where these sort of systems are finding applications? Is that something that has gone far enough yet?
So I think, yeah, that's a good question. I think there are many ways people think about using these, and that is still in development. The most immediate application has to do with this one-way transport of non-reciprocal wave propagation. That is, I think, to my impression, the most important thing that people try to realize. And that is hard because, as you can see, these systems, it's harder to make it small, right? If you actually want to make a device where you have one-way edge states for mechanical waves, that's hard because here you need to break a time reversal symmetry. You need to add some activity into it. So that is not easy. And then there are all kinds of proposals of using interface states as waveguides. It's a topologically protected waveguide. It can go around the corners, things like that. I think because like if you don't require one-way transport, you just require a waveguide that is topologically protected, you don't need to break time reversal symmetry. And that's much easier to make. Yeah. There must be other applications. I think maybe Corentin will have, I think, yeah, the applications of these.
There's a recent paper by Andrea Alou where they claim they use this concept but for microwaves, so to make like antennas and transistors, like you could put in for like 5G, you know, or 6G, whatever like antennas for microwaves, I think. And there they really are getting close to something that could be applied for, you know, telecommunications and the microwave, because there they have ways to break this time reversal symmetry by modulating in space and time. And so I think they are close, but that's not mechanics. So.
Mm-hmm. Yeah, and then I think from another direction, which is like just me thinking about this, it's not like there are real work done. One special feature about these topological states is that there is a topological protection, right? You can put in disorder, you can do a lot of random things. As long as you don't change the degree of covering, the edge mode must be there. So then you can say that there are other robust phenomena in nature, like in biology, right? In biology, there are all kinds of robust phenomena. Does any of them have a topological origin? I don't know if there is an answer to that question, but if anyone knows, I will be very happy to hear about it.
Well, I can think about allostery, in which there are models that shows that, you know, allostery means that you do something here and something happens very far away in proteins. Yeah. And we have shown, for example, that there is a model where it seems that what's happening in those type of proteins can be a type of an edge mode, because nothing happens during I mean, a big part of the protein, which is in the case was a random network, and then something happens on the other side. So I mean, it's just a model for the
That's a very good point. I think it might have something to do with the Maxwell lattice type of topological states, or maybe even this. Yeah.
And if I may add to that, there's also a recent paper by Maha and his postdoc Shang. I don't remember the name of his postdoc, where they saw that the singing saw.
Yeah.
The reason why the singing saw has a very high quality factor is because in the inflection point of the singing saw, it actually is a topological mode, and they could show that's based on, you know, plate theory and so on. So, you know, so maybe we can make topological music in the future, or maybe we are and we don't know it yet, I guess.
Yeah, that's another very nice example. Yeah. Okay. Okay, so next I'm going to just give a little more review on topological Maxwell lattices, which is another class of topological mechanical states. Okay. So just to review a little bit, I'm going to go through this and stop me if anything is not clear, because it's harder for me to gauge what everyone already knows, right? So for a mechanical lattice, you can write these linear transformations to describe the mechanical response. I think Corentin already talked a little bit about the C and Q matrices, right? So the C matrix, okay, I think I should not write it equal to 0. I will just write it more generally here. So C dot U is E, and Q dot T is minus F. So this minus sign is a convention, which I don't think we need to go into. U are site displacements. So if you have n sites, each of them is a point in d-dimensional space, you have dn times d dimensional vector that describes the displacements of all of the sites. And E is a vector for bound elongations. Okay, so if you have NB bounds in the system, it's an NB dimensional vector. So this is the so-called compatibility matrix that describes the kinematics of the lattice. And then this T are tensions on bounds. It's a NB dimensional vector. F are forces on sites. It's an n times d dimensional vector. And you can easily show that C and Q are transposed to one another in real space. Okay? So if you have a Maxwell system, which means in the bulk, NB and n times d are the same, right? So when you write C and Q matrices in momentum space, it's a square matrix, okay? And then this comes to the point where in this seminal paper by Ken and Lubinsky, they defined this way of writing the so-called chiral Hamiltonian, which is constructed from the C and Q matrices. So you put the Q matrix here and the C matrix here. You construct a Hamiltonian of dimension NB plus ND, okay? And then the square of this Hamiltonian has this, this is a dynamical matrix, and this is a so-called supersymmetry partner of the dynamical matrix. But we just need to use this Hamiltonian, okay? And when you solve for eigenstates of this Hamiltonian, remember Q acts on T, right? And the C acts on U. So the eigenvector of this would be a vector that is made of first a number of columns, a number of rows of bound extensions, and then a number of rows about the site displacements. Okay? You make a long eigenvector like that. Is it clear? And then you can see that there are a number of properties. This looks pretty much like the two-band model Hamiltonian we just wrote there, which I just erased. I'll just write it here. Yes?
Which has Q on the right? It seems that it's acting on the site displacements. So it's 0Q, then it's size TU, and it seems like it's QU.
You're right. I think I wrote it. It should be UT, not TU. Thank you. So you may ask, why do they construct a Hamiltonian in this weird way, right? Why do you put C and Q on the off-diagonal components? So it has some relation with what we talked about on the 1D chain last class and this class. So remember for that simple 1D chain of the AB springs, you have a dynamical matrix that look like this. Right? And we said that these Ks are not important. It's just a constant shift. All of the information is, I think this is Z bar. Oh, wait. This is minus Z. So all of the information is in Z, right? So because the wave functions, remember we solved that, are this something like this. So Z controls everything, and when you write it into that three-dimensional vector of D, dx and dy come from Z, right? And then when you compare it to this, it is actually quite a similar construction. You put your Q matrix in the place here. And that is, it's the same type of topological states that applies. What is special here is that you have these diagonals to be 0. And you have this chiral symmetry, which makes, I'm going to talk about that in a minute, but basically it guarantees that the edge modes are exactly at 0 frequency. It's right in the middle of the two bands. So here you have positive and negative bands. When you construct this, you have bands like this. And it's symmetric up and down. And the edge modes are all here. Okay? So what do we mean by this chiral or particle hole symmetry? We talked a little bit about chiral symmetry. In that 1D chain case, we say that it's the same as dz equal to 0, so that the path can only be on the equator, right? So you can define a topological winding number. It's essentially the same thing here. I think I copy-pasted this equation from the paper. They wrote it as tau z, but tau z is the same as sigma z, okay? And why this anti-commuting relation between the Hamiltonian and the tau z tells you that eigenvalues has to appear in plus and minus pairs. Can anyone show this relation? So firstly, you can verify that this particular H anti-commutes with sigma z. You have H sigma z plus sigma zh to be 0. It's just like 2 lines of math you can verify. But then they said that when you have this relation, it tells you eigenvalues appears in pairs. How do you show that? Yeah, you can act this on an eigenvector, right? So if psi is an eigenvector, if psi is an eigenvector, H psi is E psi, right? And then you can do H sigma z psi. This equal to, because they anti-commute, this means that for any wave vector psi, you can construct another wave vector, which is sigma z psi, that has the negative of the eigenvalue. So they must appear in pairs. And the result of that is that if you have edge modes, they must appear in pairs right in the middle of the two bands. Okay? So at the same time, this Hamiltonian also has time reversal symmetry. So if you go to the classification table of the topological states, you will see that it belongs to the so-called class of BD1, where you have integer valued winding numbers, very similar to what we talk about here in the 1D case. Okay? So then they show that you can define a winding number similar to what we did from the integral of the Berry connection, and then it can be written in this way. So the edge modes that correspond to this winding number are the 0 modes and the states of self-stress. So this is the so-called Maxwell-Caladine counting index theorem. So I think maybe it's a good point to stop here. On the next slide, I'm going to explain mechanically why this the bulk edge correspondence for this mechanical problem. Why, when you calculate such a winding number, it tells you there is a zero mode or a state of self-stress on the edge and the interfaces of this lattice. It takes a little bit of math, but we can do it in a few slides. Okay? Any questions at this point? Yes.
Hi. So Xiaoming, could you repeat what was the consequence of the time reversal symmetry, please?
The time reversal symmetry,
The BDI class. How did that come through? I guess?
so I'm, again, not a real expert in this. I think you need the time reversal symmetry for it to be in this class. So that I think one consequence is that you have this Z topological index in 1D and no new topological index in 2D and 3D. So this kind of thing cannot give you one-way edge states, in short. Yeah. Any other?
Okay, so let's thank
Okay.
Xiaoming.
Thank you.
Cough break, and we'll be back at 11:30.